This video is all about the derivative. So let's start by defining what a derivative is. We're going to talk about the derivative of a function f of x. And in terms of notation, it's written like this. And when we read this, this apostrophe is pronounced as prime. So we actually read that as f prime of x. That's the derivative of f of x. So what f prime of x represents a couple of different things. It's the slope of the tangent line to the curve f of x. And it also represents the instantaneous rate of change of our function f of x. So let's make a connection between these two things and understand how f prime of x can both represent the slope of the tangent line and talk about the rate of change of a function. So let's suppose that we have the graph of a function, say y equal f of x, so our function looks like this. And let's say we draw a tangent line to that curve at some point. So let's think about the slope of the tangent line here. The slope of the tangent line is negative, and that actually corresponds to the function decreasing. So in that way, the slope of the tangent line can tell us something about how quickly our function is increasing or decreasing. If our function were decreasing very quickly, let's say something like that, we were to draw the tangent line at a point along that curve, what we would see is a steeper slope. And then we've got this situation where, say, our function is increasing, like that. It's going up as we go from left to right. If we draw the tangent line, say at this point, now we've got a positive slope. So the slope of the tangent line corresponds to the rate of change of our function. The sign of the slope, if it's negative, indicates that our function is decreasing. If it's positive, indicates that our function is increasing. And the actual magnitude of the slope, the bigger it is in absolute value, means you've got a steeper curve. Okay, so f prime of x will represent both of those things, slope of the tangent line and also the instantaneous rate of change of our function. When we say instantaneous, we just mean the rate of change of our function at a specific point. Great, so we've got a formula back from our previous section on how to find the slope of the tangent line. And what we're doing here is just introducing this new notation. Now we know we're calling that slope f prime of x. So we're going to say f prime of x is, and then we're just bringing out the limit definition from our previous section. So it's the limit as h goes to 0 of f of x plus h minus f of x all over h. So we're going to practice using the limit definition to find f prime of x in this video. Just a little piece of terminology before we jump into our first example. In calculus, you'll often see the terminology asking you to differentiate a function. And when we say differentiate a function, that's just a fancy way of saying find the derivative. So to differentiate f of x means to find f prime of x. So we'll watch out for that terminology throughout the video. With that, I think we can jump into our first example here. So here's our problem. F of x is 2x cubed minus pi. We are going to find the derivative, f prime of x, and we're going to evaluate that at a specific x value after we've done the problem. There's a hint to go along with this. We've got a reminder here for how to expand the cube of a sum. So let's get into the calculation. Okay, we'll start by finding f prime of x. So we're going to say f prime of x, according to our limit definition, it's the limit as h goes to 0 of f of x plus h minus f of x all over h. So same formula as we saw in our previous section. At that point, we were just calling it the slope of the tangent line, but now we know that we can call this f prime of x, or we can say conceptually that represents the instantaneous rate of change of our function, if we want to think of it that way. All right, so if we were to sub in h equals 0 here, we would get 0 over 0. So that tells us we need to do more algebra. And the algebra we're going to do is actually plugging into our function. So let's think over on the side here, what would happen if we wanted f of x plus h? Well, we would need to look at our function. Here it is. And let's replace every x that we see with an x plus h. So we would have 2 times x plus h all cubed minus pi. So that expression there is our f of x plus h. And we're going to write that into our numerator here. So 2 times x plus h all cubed minus pi. And then we need to subtract off f of x. So subtracting off 2x cubed minus pi, and then dividing that whole thing by h. And let's continue with our calculation. So we're talking limit as h goes to 0. Well, if we were to plug in again, we'd still get 0 over 0, so more algebra required. We've got this hint at the top of the page for how to expand the cube of a sum. So that's actually the next thing that we're going to use. We're going to keep the 2 out in front here. We're going to give ourselves square brackets, and let's just write down what x plus h all cubed looks like. So according to our formula, just replacing the a with an x, the b with an h, this would look like x cubed plus 3x squared h plus 3x h squared plus h cubed. Okay, and then we've got a minus pi, minus 2x cubed, and a plus pi. And that's all over h. Great, so already we've got a little bit of cancellation here. You can see the minus pi and the plus pi will cancel. Next thing we're going to do is just distribute that 2, and then we'll start to get quite a bit of cancellation and cleaning up that can be done. So we'll have 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed, and that's still minus 2x cubed, and then all over h. Okay, so the 2x cubed and the minus 2x cubed can cancel. And now notice every single term in the numerator has an h in it. So that's going to allow us to do a little bit of factoring, and then we can cancel an h from the top and the bottom. So notice at this point you still get 0 over 0 as you sub in h equals 0. So we're trying to clean this up and get to the point where we're taking the limit as h goes to 0 of a continuous function. That's our goal. All right, so let's do the factoring on top. Pulling out a factor of h, we'll have 6x squared plus 6xh plus 2h cubed, or 2h squared rather, after we do the factoring, and then that's all divided by h. So we can cancel that factor of h from the top and the bottom, and we've now just got this nice 6x squared plus 6xh plus 2h squared. So this is the very first step where it now makes sense to actually evaluate this at h equals 0. We no longer need the limit sign because we're actually going to sub in here. Plug in the h equals 0, and this term disappears. This term disappears, and what we're left with is 6x squared. So that is our derivative. And let's go back to our other page and just finish off the problem. Okay, so here we are. Remember that the question was actually asking us to do 2 things. So it was asking us to find f prime of x. So we've done that. We've said f prime of x is equal to 6x squared. And then once you've got that formula, see, then you can plug in any specific x value if you want to get the slope of the tangent line at that specific point. So for example, if we sub in x equal -1, we get positive 6. Okay, so that's telling us the slope of the tangent line to the curve y equal f of x, and it's also giving us a sense of the rate of change of our function. So a little piece of terminology here. We're going to say that a function, f of x, is differentiable if the derivative, f prime of x, is defined. So let's practice that terminology just in the context of this previous example that we just did. So let's call this a quick example and just refer back to what we just did. So in our previous example, we found the derivative to be 6x squared. So we did that up there. So f prime of x is equal to 6x squared, whereas the original function was 2x cubed minus pi. So we can look at our derivative here and we can say f prime of x is 6x squared. That's defined for all x. If you put any real number in there, you get a nice real number value. So f prime of x is defined for all x. And what that means is that our original function is differentiable for all x values. So we're just practicing this idea that a function being differentiable means the same thing as the derivative being defined. Before we go into our next example, we need a quick recap about common denominators. So let's do that on a fresh page. So let's say we have this expression here, 2 over x plus h minus 1 minus 2 over x minus 1. And we just want to practice simplifying this because this is what we'll need for our next, for one of our next examples. So the idea is to create a common denominator. So we're going to multiply the first term top and bottom by the missing factor, which is the x minus 1. So multiply top and bottom. Bottom here we'd have x plus h minus 1 times that missing factor, which is x minus 1. Okay, and then for the second term, we're going to go minus 2 times x minus 1, and that's going to get multiplied by the missing factor from the other denominator. So the x plus h minus 1. So that way we're creating this common denominator of x plus h minus 1 times x minus 1. Okay, now some people will do this all in one step, particularly when there's only 2 terms in the expression. They might just say, okay, I'm going to create the common denominator of x plus h minus 1 times x minus 1. And then the fast way to think about that is just cross multiplying. So you'd multiply these guys together, have 2 times x minus 1, and then you'd say, well, we have a minus 2 times this guy, x plus h minus 1. So that way of thinking about it works particularly well when they're just 2 terms. But if you had, say, 3 terms, you know, some fraction plus another fraction minus another fraction, then this process of just thinking about what factor is missing and multiplying that on the top and the bottom is really the rigorous way to go. So in terms of getting this simplified, we're trying to do 2 things here. We're going to expand the numerator. Our goal is to get something nice and simplified in the numerator, and we want to keep the denominator factored. And that's actually good news because that means there's nothing you need to do to the denominator. So just keep the denominator as is, and we're going to expend our energy just in getting that numerator cleaned up. So let's expand everything out. We'd have 2x minus 2 minus 2x minus 2h plus 2 on top. Denominator stays factored. And then let's look for a bit of cancellation here. So the 2x and the minus 2x will cancel. The minus 2 and the plus 2 will cancel. And we'll be left just with minus 2h on top. So we can write a cleaned up version of our answer. So minus 2h over that product in the denominator, x plus h minus 1 times x minus 1. So that's a little flashback to simplifying, just in case you didn't quite remember that from your previous math courses, or in case it's been a little while. That's going to help us with some of our upcoming examples. So here's our next example. We're going to jump into a fresh page to do that. So here's our function. F of x is x squared plus 4 over x, and the problem is to find f prime of x. Some alternative wording that you might see, instead of seeing the problem written this way, you may also see it written as just differentiate the following function, and then you'd be told what f of x is, something like that, because to differentiate means to find the derivative. So 2 different wordings to watch out for. I'll just revert to the original wording here, and then we'll proceed with the problem that way. So what we're trying to find here is the derivative f prime of x, which tells us about the slope of the tangent line and also tells us about the rate of change of our function. So let's jump into the calculation. So we're going to set up the limit definition of the derivative. We'll take the limit as h goes to 0 of f of x plus h minus f of x all over h. And we need to do as much algebra as possible until we get something other than 0 over 0 for this expression. Okay, so first thing we will do is figure out what it looks like when we put x plus h into our function. If we like, we can do a little bit of scribbling on the side here. So let's look at our function, which is x squared plus 4 over x, and let's replace every x that we see with an x plus h. So we'd have x plus h all squared plus 4 over x plus h. All right, so for this one, it's particularly nice to have done that over on the side so that we can sort of see what's going to happen in advance. This expression that we're looking at inside the limit is going to have some stuff that's all over h. We've already figured out that this f of x plus h also has a fraction in it. So it's like a polynomial plus some other fraction here. I'll just write the details here to show that's a fraction. So this is looking a little messy already because we're going to have a fraction that then has to be further divided by h. So in order to make life easy, usually what we do in this kind of situation is we'll write a big 1 over h out in front, give ourselves square brackets, and that way what's going to go inside the brackets is just our f of x plus h minus f of x. That way we avoid doing this double division thing. So f of x plus h looks like x plus h all squared plus 4 over x plus h, and then we're subtracting off f of x. So we need to subtract off both terms from f of x. So those terms should both be negative there if we're careful about our signs. Great, so we're going to keep this limit expression on here, limit as h goes to 0. We're going to keep the 1 over h out in front, and let's work on simplifying this. So what I would do is group the polynomial parts together. So let's group the x plus h squared minus x squared. Let's group those guys together. And then let's group the fractions together. 4 over x plus h minus 4 over x. Okay, and that will help us figure out how to proceed in terms of our algebra. So limit as h goes to 0 of 1 over h times all this stuff. Well, let's start with the first two terms. We're going to expand the square to get x squared plus 2xh plus h squared minus x squared. So we'll have a little bit of cancellation there. And then for these guys, we need to do our common denominator thing that we just practiced. So everything's going to go over the common denominator of x plus h times x. And we saw from our recap there that we can just think about cross multiplying to figure out what our numerator is going to look like. So we'll have 4x, and then for the second term, it's actually a minus 4 times an x plus h. Okay, so that's the quick way to get that part done. And then let's start simplifying. So x squared and minus x squared are going to cancel, and we can start to clean this up gradually. So limit as h goes to 0, 1 over h times 2xh plus h squared plus, let's do a little bit of simplifying in this fraction. So remember what we said in our recap, you want to keep the denominator factored. So just leave that denominator alone. And let's clean up the numerator. So we'd have 4x minus 4x minus 4h. And then the nice thing here is that the 4x and the minus 4x will cancel. So we're really just getting minus 4h for that numerator. Okay, so now we're in the home stretch. I got the limit as h goes to 0 of 1 over h times some stuff. And the goal is always to get a factor of h that can be pulled out from this expression in the numerator. So let's pull an h out of everything. I'm going to draw round brackets here. stress factoring out that h, be left with 2x plus h. And then when you're factoring a fraction like this, you just need to pull an h out of the numerator. So we're going to go minus 4 over x plus h times x. So I guess just a little kind of algebra pointer over on the side here. Let's say you had something like 32 over 13. If you wanted to pull a factor of 2 out of that, you're just pulling a factor of 2 out of the numerator. So you'd say that's 2 times 16 over 13. It doesn't affect the denominator, you're just pulling it out of the numerator. And I point that out because that's really what's going on here. Pulling a factor of h out of this fraction here, we just need to pull it out of the numerator. Okay, so now things are looking really good because we got this nice factor of h in the top and the bottom that can cancel. See this h that we've got inside the brackets, you could even think about moving it and putting it out here. That's like saying you've got h over h times all this stuff. So that h from the numerator and h from the denominator will cancel. And we've now got limit as h goes to 0 of this stuff here. So this is the very first step where it makes sense to plug in h equals 0. We no longer need our limit sign. So we're going to evaluate at h equals 0. We get 2x plus 0 and then minus 4 over, well, x plus 0 is just an x. So we've really got x times x in the denominator there. Or if we write that, you know, in the simplified way, 2x minus 4 over x squared is our answer. So let's come back to the problem and we'll just do a little bit of follow-up with that. So here's our answer right at the bottom of the screen. And so if we think about what real numbers make sense to put in here, you can put any real number you like in there except x equals 0. X equals 0 is going to cause a problem in the denominator here. So we say f prime of x is defined for all x not equal to 0. And to say that your derivative is defined is the exact same thing as to say your original function is differentiable. So f of x is differentiable for all x not equal to 0. So that's just a little bit of practice with our terminology. Okay, a couple more examples to go. For the next problem, we're going to do a limit example. We're not even going to talk about derivatives in this problem. Essentially, this is kind of a gateway to our last problem. So there's just something, a little algebra point that we want to practice before we get into our last problem. So let's flip into a new page and try this. So the problem is to find the limit as h goes to 0 of root x plus h minus root x over h. This is our first time doing one of these limit problems with square roots in there, so we're just going to practice the algebra that's required. Okay, if you tried subbing in h equals 0, you would get 0 over 0. So there's some sort of algebra required here, and we'll see what that algebra trick is in this next step. So we're going to take limit as h goes to 0. We're going to recopy our expression exactly as it was written there. And the trick is to multiply this expression, top and bottom, by a certain quantity. Okay, so the certain quantity is exactly what we're seeing in the numerator, but just with the sign changed. So instead of having root x plus h minus root x, we're going to actually have root x plus h plus root x. Okay, and whatever we multiply the top by, we have to multiply the bottom by the same thing. So multiplying the bottom by root x plus h plus root x. So effectively, this is just like taking a fraction. You can multiply it by 2 over 2, or you can multiply it by 7 over 7, or a million over a million. So you're not changing the value of the fraction by multiplying top and bottom by this strange thing. But we'll see that this strange thing is exactly the right choice for what to multiply by, so that we get some really nice cancellation. So you may remember from pre-calculus that this expression here, this sum of roots, that's called the conjugate radical. Conjugate radical. So radical, just a fancy name for an expression that has roots in it. And conjugate is the expression for when you take a quantity, particularly when you've got two roots in that quantity, and you just change the sign of what you're seeing in the middle. So take that minus sign, turn it into a plus sign. That's the conjugate. So the conjugate radical. That way, when you're reminding yourself of what this trick is, you can remember it kind of conceptually, or you can remember it in words, and you can say, oh yeah, I'm supposed to multiply the top and the bottom by the conjugate radical. So let's see why multiplying top and bottom by this conjugate radical works so well. So we've got the limit as h goes to 0. In the denominator, we're just going to keep everything factored. So h times the conjugate radical. And what we're really interested in is what's going to happen on top. So let's imagine foiling this out. If you want to be super clear here, you can just give yourself a set of brackets, draw them in black just so they're really clear, a set of brackets around all this stuff, so that we realize that we need to FOIL this out. Okay, so we're going to multiply the root x plus h times a root x plus h. So continuing our FOIL process, we would then have the outside terms, so the root x plus h times the root x. I need a bigger line, division line here. And then continuing to FOIL this out, inside terms, you'd have a minus root x times a root x plus h, and then last terms you'd have a minus root x times root x. Okay, so let's see all the magic that's going to happen here. Remember that if you multiply something like root 2 times root 2, you're going to get 2. If you multiply root 3 times root 3, you're going to get 3. So if you multiply root x plus h times another root x plus h, all that's giving you is x plus h. Okay, now inside terms are going to cancel. The root x plus h times root x cancels perfectly with this minus root x plus h times root x. And then at the back here, we've got a minus root x times root x. So that's just going to give us a minus x. Wow, so that actually simplifies really nicely. Let's get this cleaned up, and we're pretty much in the home stretch here. So we're talking limit as h goes to 0 of, we've got x plus h minus x, and then in the denominator, h times a bunch of stuff, our conjugate radical, root x plus h plus root x. Okay, so what's going to happen on top here, x's are going to cancel, and then I think just to avoid doing too much in one step, I'll do this in the next step, but you can probably see that the h's are going to cancel as well. So you've got h over h times some other stuff. Okay, and you can think of that h on top as being h times 1. So factor of h cancel from the top and the bottom. And this is where we're actually going to be able to evaluate the limit now in our next step. So we've kept our limit sign on there. We're trying to figure out the limit as h goes to 0. At every previous step, we had 0 over 0. But now that we've managed to cancel that factor of h, we've got a nice 1 on top, and we've just got our conjugate radical in the bottom. So let's drop our limit sign. We're actually going to plug in h equals 0, and we're getting 1 over, well, this guy would be root x plus 0. Okay, so might as well call that root x. So 1 over root x plus another root x. And then final way of cleaning this up is just to say, well, normally we would collect the like terms in the denominator and just say that's 1 over 2 root x. Okay, so we are done that limit problem there. I'll come back to our notes. So there we go. And really that was a warm-up problem for our last derivative calculation that we're going to go into now. So given this function, let's find f prime of x, and we'll do that on a new page. So we're given the function root x plus 3, and we're going to find the derivative f prime of x. Remember some alternative wording that could come up here. Often in calculus, we like to use the terminology differentiate for the process of finding the derivative. So someone could just say differentiate f of x equal root x plus 3, and that means exactly the same thing. Just find f prime of x, however it's worded. Okay, so let's start by saying f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the limit as h goes to 0. Let's take our f of x up here and replace the x with an x plus h. We would have root x plus h plus 3 minus root x plus 3 all over h. Now, at this point, this kind of reminds us of the previous problem. So you can see how the previous problem was really just the warm-up to figure out the algebra that's required to solve this problem. So we know from our previous discussion that we need to multiply top and bottom by the conjugate radical. Now that we've had a bit of practice with that, we can probably do that a little bit faster. So top and bottom get multiplied by the conjugate radical. Okay, let me recopy the first term here. So we got root x plus h plus 3 minus root x plus 3. Our conjugate radical is this exact same thing, but just with a plus sign instead of a minus sign. So it's root x plus h plus 3 plus a root x plus 3. Okay, and then whatever we multiply the numerator by, we need to multiply the denominator by that exact same thing. So root x plus h plus 3 plus root x plus 3. Beautiful. So we're going to do some FOILing on top, talking about the limit as h goes to 0. Let's FOIL this stuff out. We know that when we multiply the root with itself, we're just going to get the full x plus h plus 3. We know from previous experience, from our previous problem, that when we do the outside terms, you're going to get something like plus a certain root times a certain root, and then you're going to get minus a certain root times a certain root. These guys are going to cancel. And then we'll have a minus root x plus 3 times another root x plus 3. So that's just going to give us a full minus x plus 3. The thing I would be careful of here is just the bracketing, because we do need to make sure that both the x and the 3 are being subtracted off. Okay, so that's how I would approach that numerator there. And then the denominator, we're just going to keep it factored. So h times the conjugate radical, root x plus h plus 3 plus root x plus 3. Okay, and now we're getting somewhere. See, we're going to have a lot of nice cancellation in the numerator. We've got this x plus 3. That's going to be perfectly cancel with the minus x plus 3. So we've now really just got an h on top. Let's do our next step on another line. So we've got h on top, and on the bottom h times the conjugate radical. So root x plus h plus 3 plus root x plus 3. Great, so now the factor of h is going to cancel from the top and the bottom. So think of that numerator as just being h times 1. So when we cancel the h, we've just got a factor of 1 on top. And this is the very first step now where we can actually evaluate. So we're going to drop the limit sign. We're going to plug in h equals 0. And what we're getting, 1 over root x plus 3 plus another root x plus 3. And remember, if you have something like, root 7 plus root 7, we would just collect those like terms, and we'd say, oh, that's 2 times root 7. So that exact same thing is going to happen in the denominator here. You've got a root x plus 3 plus another root x plus 3. That is just faster to call that 2 root x plus 3. So that is our answer to the problem. So 1 over 2 times root x plus 3. So let's come back to the main page there where we did that. So we successfully found f prime of x. That tells us the slope of the tangent line to our function f of x. It also gives us a sense of how quickly f of x might be increasing or decreasing. So let's just practice our terminology around what it means for a function to be differentiable. So this f prime of x, if we think about what numbers we could put in here, you wouldn't want to put -3 in there because then you'd have a 0 in the denominator. You wouldn't want to put anything more negative than -3 because then you would start to get negative numbers under the square root. So you could put any x value that's strictly bigger than -3 in there. So we can say f prime of x exists for x bigger than -3. And to say that f prime of x exists is exactly the same thing as to say the original function that we started with is differentiable. So f of x is differentiable for x bigger than -3. So last thing we're going to talk about in this section is just a little bit of notation. 2 common ways to talk about a function. We can either say f of x equals something, or we can say y equals something. And we will use both throughout the course. The 2 notations have slightly different strengths and weaknesses. So one is good in one context, one is good in another context. So we'll get used to both. And we've just been practicing the idea of the derivative. So we have introduced the notation f prime of x for the derivative. If we went through the whole limit definition calculation for this particular example, we would find that the derivative f prime of x equals 2x. What we want to practice here in terms of notation is just a few different ways of writing down that derivative. So f prime of x is one way to write it. There are actually a few different ways to do it. So if you were calling your function y, you might prefer to call the derivative y prime. So I'm actually going to change the highlighting here a bit. Just focus on the notation. So f prime of x, one way to say the derivative, y prime, another way to say the derivative. It means exactly the same thing, just slightly different notation. Third way to say it, we'll talk about this a little bit later on in the course, df by dx. So we read that df by dx, and in words you can say the derivative of f with respect to x. This way of doing it is particularly useful in any problem where we have a couple of different variables going on. Like let's say we were talking about a cylinder and we were paying attention to both its radius and its height. That would be a situation where we might want to use this kind of notation. The derivative of f with respect to x, we're talking about how quickly is our function changing with respect to the variable x. Little variation on this, if you were calling your function y instead of f, you could just modify that to say dy by dx. In either case, you're putting the name of the function on top. You're saying d function divided by d variable. So we've now got 4 ways of writing down the derivative. Fifth and final way, if for some reason you wanted to be just really crystal clear about what your function is, you could put your actual function into the brackets, and then you could say d by dx of this function. Now, sometimes we want to plug in a specific x value into our derivative. So depending which notation we're doing, there are different ways to actually plug in, and I think I'll show these just side by side. So if we wanted to plug in, say the x value 1, we could say f prime of 1 would give us 2. If we were calling our derivative y prime, we would write something like y prime evaluated at x equal 1. So we would just use this vertical bar to show that we're plugging in, and then say x equal 1. We'd say that's equal to 2. Similarly, if you were using the d notation, so you could go df by dx, you just say evaluated at x equal 1 like that is equal to 2. Similarly here, you could go dy by dx evaluated at x equal 1 equal 2. And honestly, for this notation here, not really common to try to evaluate using that notation. We would use one of the 4 previous notations if we were trying to plug in a number. So just as a visual to wrap this up, let's remember that all these expressions just represent slope of the tangent line. So our function here was the familiar parabola, good old parabola, y equal x squared. And when we're talking about f prime of x, we're talking about the slope of the tangent line. So we can plug in any x value that we like and figure out the slope. If you decide to plug in the x value 1, then you're looking specifically at the point here where x equal 1 and figuring out the slope of the tangent line at that point. So according to our sketch, 2 seems to be a reasonable value for the slope of the tangent line. So that's all about the derivative. Thanks for watching.